Hi guys, this is Dr. Schultz, and this video lesson is on the complete torque formula. So it's going to be a short lesson, but I would expect that you guys will take notes on this, and so let's go. So in our example so far of torque, we have looked at examples involving forces which basically are perpendicular to the lever arm. So in my picture here, this is going to be the lever arm, R. This is my pivot. I'll just put a P there for pivot. And of course, this is the force. And like in the activity that we did and some of the problems that we've solved, we've always made this a 90-degree angle. And so when you want to find the torque from this situation, you would say that the torque would be equal to R times F. And you would just multiply those two numbers. So we want to get a little more general in terms of our thinking, because sometimes the force does not make a 90-degree angle. Sometimes the force makes some other angle. Okay? So for example, let's take a look at, what if you had a force that does this? Okay, so it's kind of not really pulling straight down on that lever arm anymore, but now it's making some new angle. Okay, and so there's got to be some way of dealing with that. And so the way to think about this before I show you the formula is to think about the components of the force. Okay, so remember, components are kind of the x and the y pieces of a vector. And so if you have a force here which is a diagonal, I hope you can see that it's actually going to have a component in that direction which goes perpendicular to the lever arm. And it's also going to have a component which goes this way. And that component is parallel to the lever arm. So I'm going to label those. This one here is the perpendicular component, so we'll give it the perpendicular sign from geometry. And this down here would be the parallel component, so we'll give it the parallel sign. Now, if you look at that, remember, components are a way of thinking about vectors where you can replace the original vector with two pieces, and you can think about what the pieces would do. So let's look at the parallel component first. If you have a force which pulls directly out on the lever arm, that force is not going to create a torque. And a good analogy would be if you think about a door. Like if this is a door that you're looking at, and here's the hinge, here's the door, and then you grab the door knob and you pull straight out on the door. I mean straight out like this way. The door is not really going to have any tendency to rotate. In other words, no torque. So I'm going to put no torque from that component. The component that does give us the torque is the perpendicular component. And of course that one is the one that makes a nice right angle. And if we knew that component, we could then say that the torque would be given by the radius times the perpendicular component. And that would give us the torque in that situation. So the question is how do you find that component? And this goes back to trig. I know you're groaning right now, but deal with it. In trig, if you have a vector like this, and you want to get its components, and you know an angle, then you can use the angle to find the components, but you have to remember SOHCAHTOA. Okay? So, if you recall SOHCAHTOA, what we want to get here is we want to find this component, okay, which is also corresponding to this side of the triangle. And we want to relate the hypotenuse to the opposite side. We want to relate the hypotenuse to the opposite side hypotenuse, opposite, we got to use the sine function. So the deal would be that if I take the sine of the angle, that's going to be the opposite divided by the hypotenuse. And so the perpendicular component that we're looking for is going to be found by multiplying the diagonal times the sine of this angle. Okay? So if you know the angle there and you know the diagonal, you can find the perpendicular component and then you can plug that back in. So I'm going to rewrite the torque formula and I'm going to just build this into it. So I'm going to rewrite this now and I'm going to say the torque is equal to R times F perp, so it's going to be R times F perp, which is R times F times the sine of the angle. And that is the complete torque formula, because that's going to let you get solve for the torque that you want if you've got an angle. Okay, so let's do a quick example. Let's take an example where we have a pivot, and let's do a lever arm of 0.5 meters. And then I'm going to have a force of 100 newtons. And I'm going to make this angle 36.9 degrees. So what angle am I talking about? I'm talking about extending the lever arm. This dashed line is supposed to extend it. And 36.9 degrees is the angle above that. Okay. So, what would the torque be in this case? So let's see. Torque is equal to my lever arm of 0.5 meters multiplied by my force of 100 newtons multiplied by the sine of 36.9 degrees. Okay. So we pull out our calculators. Let me go get mine. And I want to, let me do the sine of 36.9. Oops, I think that's in radians. So you might want to check this. Make sure that in your mode, you are in degrees mode. That would explain that. And the sine of 36.9 is 0.6. Okay? So this is 0.60. 0.5 times 100 times 0.6. All right, so 100 times 0.6 would be 60. Half of 60 would be 30. And the units would be meters times newtons, but we like to write newtons times meters so we don't get confused on that. So that's my torque. And then I go back and I look at this and I would say, hey, that lever arm is going to rotate in the counterclockwise direction. And so I definitely want to write that down. Okay. By the way, I didn't say this the other day, but when a torque is counterclockwise, we make it positive. Okay. So you might just add that to your notes, that CCW always gives positive torques, whereas clockwise always gives negative. So I always like to write CW or CCW, but putting plus or minus also is something which the pros do, and you'll see that it's a useful thing later on. All right, so that is how you do the complete formula for torque. I think it's pretty straightforward if you think about it. Oh, and one more thing. How do you know which angle to use? Okay, because what if you have a problem where they give you this angle instead of 36.9? Well, let me figure out, what is that angle? That would be the supplement. That would be 180 minus 36.9. That's 143.1. degrees. Okay, and you might be wondering, oh my gosh, what if I use 143 degrees instead of 36.9? Is that going to mess everything up? Well, why don't you try it right now on your calculator? Try to take the sine of 143.1 degrees. Okay? And, amazingly, maybe, you get 0.6. In other words, you get the exact same thing that you got the other way. And so maybe you remember this from math class, but supplementary angles give the exact same sign. And so, hey, this is actually useful now in physics. So what we're saying is that the sine of this angle is equal to the sine of 180 minus that angle. And that's a math thing, but it also helps us in physics because then you're not likely to make a mistake by picking the wrong angle. So that is how you use the torque formula, and yes, you'll get to practice that on some problems that I gave you. So have fun.